So now we're going to start using some of the trig identities and the substitutions we can perform so that we can set up an equation to make it easier to solve when it has trig functions in it. You'll still want to have your trig reference sheet handy for while we're doing this. Here are some guidelines for while you're trying to solve the trig equations. The first tip I have for you guys is to make sure you do as much simplifying as possible. A lot of times I still like to break things into sine and cosines if I can, get common denominators or clear fractions whenever I can. And make sure you're following the same rules for solving equations that you normally do. If you add a number to one side, you have to add it to the other side as well. Same thing with multiplying. If you multiply one side by sine, you have to multiply the other side as well. Now, when you get down to the very end and you get some kind of an answer like sine of x is equal to 1/2, then you're going to want to refer to your unit circle or trig chart either way and find when is the sine of x value equal to 1/2. So for the unit circle, check the y coordinates, find the ones that equal 1/2, and then state what the angle measurements are. That's what x is representing in this case, the theta values or the angles. One thing that's frequently forgotten is to check for any solutions that would be extraneous. So if you get an answer of 0, for example, but in the original equation that you were given, it would have made the denominator equal to 0, for example, then you would have to actually exclude that answer since it's what we define as extraneous. So anything that makes your equation undefined, you have to cross those answers out. And the last comment I have here is sometimes a question will say give all of the answers in a given interval, which is what I was talking about earlier. Usually it'll specify between 0 and 2 pi, for example, so you don't have to keep going around and talking about answers like 3 pi and 5 pi and 7 pi. But if they just ask you for all of the solutions, then you need to include all of the coterminal ones. So since the unit circle goes around infinitely, if you found that pi is an answer, then that would mean 3 pi is an answer, and 5 pi, and 7 pi, and 9 pi. So basically, you would take the answer you have plus 2n pi. And that's for sine, cosine, secant, and cosecant, because that's the period for those functions. If you are dealing with a tangent or a cotangent function, the period for those is shorter. It's only pi instead of 2 pi. So it would be n times pi, where n in these cases is defined as any integer. So the idea is that you're saying, okay, if n is 1, then this equals 2 pi. If n is 2, then this is 4 pi. If n is 3, 6 pi. So setting that up basically creates the process of it going around the circle over and over again for you and finding all of the coterminal answers. Now this one specifies just the answers in the interval from 0 to 2 pi, so we're not going to have to do the plus 2n pi stuff for this one. However, I do see that there's an instance that I could replace something with a sine or a cosine value. So I'm going to rewrite tangent as sine of x over cosine of x. And I'm not going to do anything on the left side, so I'm just going to leave that as is. So I still have sine cubed and cosine a denominator. Well, now that both of these have the same denominator of cosine of x, I could actually just multiply both sides by cosine, and then we multiply the left-hand side by cosine, those would cancel, and we multiply the right-hand side by cosine, those would cancel. So if those clear out, I'm left with just sine cubed is equal to sine of x. Next, I'm going to subtract that sine of x over to the other side of the equation. It's fairly common that we try to set one side of the equation equal to 0 and then do some factoring step of some sort to break the other side down. So now between the two terms that I have, I do see that they have something in common. They both have a sine of x in them, so I can take that out using the GCF factoring technique. And if I remove sine of x from this one, I'll be left with sine squared. And if I remove sine of x from this one, I'll be left with a 1. Don't forget that you have that minus 1 there. Sometimes I see students leave that off. The zero product property lets us solve the two things in this product separately. So now I can say, when does sine of x equal 0? And when is sine squared of x equal to 1? because I'm setting sine squared of x minus 1 equal to 0, and I'm moving the 1 back over. Now this one's not quite finished because I can actually take the square root of both sides of the equation. That would clear out the exponent on this one. And then be careful about remembering when you take the square root of both sides of an equation, that creates a plus or minus answer. So I'll need to look at when does sine of x equal plus or minus 1, and when does sine of x equal 0. So first let's find the values where sine of x is equal to 0. By referring to my unit circle, I'm going to be looking for any of the y coordinates that equal 0. So I see one happening over here at 0 radians, and another one happening over here at pi radians. Those are the only two times that the y coordinate is equal to 0. So for sine of x equals 0, I'm going to say 0 and pi. Make sure you're paying attention to your interval. This does include 0 as an endpoint. That's why I have that one as an answer. And pi is also between 0 and 2 pi. For the other part of the answer, we're looking for where are the y coordinates equal to positive or negative 1. So again, you're just looking at the y coordinates going around. Here's a positive 1, so I have pi over 2 as an answer. And then if I keep going all the way around looking at the y coordinates, you should also see 3 pi over 2 as the other place where the y coordinate equals negative 1 in this case. So pi over 2 and 3 pi over 2 are the answers to this part of the solution. Now the last part, and probably the trickiest piece, is making sure to consider whether any of these four answers that we just created would make the original equation undefined. So undefined comes from having a 0 in the denominator, and tangent of x also just has some values that make it undefined at specific angles regardless. So first, let's see if any of our answers cause cosine of x to equal 0, because having a 0 in the bottom of a fraction would be a problem. Well, out of these four answers, cosine of x is based on the x coordinate, so that would mean I don't want an x coordinate of pi over 2 or of 3 pi over 2, because both of those would make the denominator of this fraction equal to 0. So I actually need to cross out the pi over 2 and the 3 pi over 2 solution. For tangent of x, if you remember the values from the table, we said tangent goes 0, square root of 3 over 3, 1, square root of 3, undefined. So again, I wouldn't have wanted pi over 2 as a solution here. And then it goes back around until it gets over here where it hits another undefined value. So we already eliminated those two answers because the cosine value was undefined for those, but they also would have been eliminated because of the tangent value, even if we hadn't had that cosine in the denominator. So make sure you consider anything that makes the denominator of your fractions equal to 0. My final solutions on this one are just the 0 and pi. That's all of the solutions between 0 and 2 pi that solve this equation. Here's another example, and notice that this time it doesn't say find the solutions within a certain interval, it says find all of the solutions to this equation. So we'll talk about that once we get down to the actual angles that we're identifying. First thing I'm going to do here is I'm going to subtract the 1 over to the other side and write this as 2 sine squared of x plus sine of x minus 1. So try to set your equations equal to 0 for solving purposes. Next, you might want to pretend that this just said 2x squared plus x minus 1, because hopefully you recognize that this equation here can be factored, and this is the exact same process for factoring with the signs in there instead. So if it helps you to visualize it, think of them as x squareds and x's for sine squared and sine instead. So I'm going to be looking for two numbers, or two binomials here, and the first terms have to multiply together to give me 2 sine squared of x, so that would be 2 sine of x and 1 sine of x. And then I need the last two numbers, in the last two spots of the binomials, to multiply together to give me negative 1. But I'm going to need the outside and the inside products to add up to a positive 1. So if I put plus 1 and minus 1 here, I have negative 1 times 1 is negative 1. And when I'm looking at the outside product, that's positive 2 sine of x, and the inside is negative sine of x. So 2 sine of x minus sine of x adds up to give you 1 sine of x. So this is the factoring used for the equation I have in blue. But like I said, if it's easier for you to factor it based on the x squared version and then just plug the sine of x's back in at the end, that's fine. So at this point, again, I have the zero product property. I have two different things being multiplied, two binomials, set equal to 0. So what I'm allowed to do is actually set each of the binomials to 0 separately. And then those equations are a lot easier to solve from there. So for the equation on the left-hand side, I would add the 1 and then divide by 2. So I'm going to be looking for where the sine of x values are equal to positive 1/2. For this equation, I'm just going to subtract 1 from both sides. So I'll be looking for where the sine of x values equal negative 1. And then we're going to refer to our unit circle or our trig chart again to find those solutions. So first, let's do the sine of x equals 1/2. That means I need to find the y coordinates that have a 1/2 value. So pi over 6 is one of my solutions, and the other one should be symmetrically around it at 5 pi over 6. That also has a y value of 1/2. So pi over 6 and 5 pi over 6 are two answers. And then for this other part of the equation, I'm going to have sine of x equals negative 1. So let's find the y coordinate equal to negative 1. That one happens down here and only down here. So the answer for that one is 3 pi over 2. Now don't forget to check for any values that would have made the original equation undefined, but since I don't have any fractions in here, and since sine of x is never undefined on its own, like the tangent function is, I shouldn't have any that I need to eliminate. However, we're not just listing the values between 0 and 2 pi. So what I have to remember is that while pi over 6 was an answer, if I went completely around the unit circle again and added 2 pi to that, that would also be an answer. If I added 2 pi again, that would be an answer. So you can do this an infinite number of times, and I'm not asking you to sit there and write out every single one of those solutions. What we do instead is we say pi over 6 plus 2n pi is an answer. This plus 2n pi piece is just taking care of the fact that I can add 1 times 2 pi, and that'll give me a coterminal angle. If I add 2 times 2 pi, that'll give me another answer. 3 times 2 pi will give me another answer just by going around over and over and over again. So for all of these, since these are based on the sine function, I just need to take the answer I found and add the 2n pi. That'll take care of the coterminal ones. So since all three of these were based on the sine function, all three of these use the plus 2n pi piece. If you remember from the notes earlier, I showed that when it's tangent or cotangent, you would just be adding n pi instead of 2n pi. So that's all for the notes today. Thank you.